Raffaele Vitolo. This is a joint talk with Paolo Lorenzoni, and you see the title. Raf, please begin.
Okay, so thank you very much, Joseph, for this invitation. It's always a pleasure to speak at your seminar. And today I will speak about recent results on the interplay between certain families of Bi-Hamiltonian systems and projective geometry. Indeed, this is a project on which I am working with several different people, mostly Paolo Lorenzoni, in recent years. And each year I have some progress and I show it around. Let me start. So these are the contents. So I would like to show that there is a correspondence between families of Bi-Hamiltonian systems which are selected by the choice of two compatible operators with the structure that you can see here in this first item. So A1 is the sum of a first-order operator and the second or a third-order operator. First-order operator is P1 and the second-order or third-order operator is Ri. And the second Hamiltonian operator of the Bi-Hamiltonian pair is just a first-order operator. Why this structure? Because such a structure is possessed by many famous Bi-Hamiltonian systems, starting with KDV. I will show several examples in the very next slides. So the correspondence will exist between such Bi-Hamiltonian systems and triples of algebraic varieties in the space of projective lines. So if you take the projective space of how to say, of which the field variables are in a fine chart, it will be Rn plus 1 or Cn plus 1. And if you consider the Blücher embedding, so the space of all lines in this projective space, then you can consider sub-varieties of this space. Such a geometric picture was introduced by Blücher around the 50s of the 19th century. Well, what turns out is that there is a bijective correspondence between triples of algebraic varieties and triples of Hamiltonian operators, which are mutually compatible and generate with the previous structure Bi-Hamiltonian systems. Some of them are very well known. Okay. So I will start with few slides recalling some basic material on Hamiltonian systems. So I will be boring for those of you who already know the subject, but I prefer to be to the safe side and be clear as much as I can. So we will consider evolutionary systems of PDEs in two independent variables and many dependent variables or field variables. Field variables are UI and independent variables are T and X. And then such systems are Hamiltonian if they can be written in this form: UIT equals AIJ calculated on the variational derivative of certain density, Hamiltonian density. This AIJ is a Hamiltonian operator. Hamiltonian operator is our main object in this seminar, and in this context, it is a matrix of differential operators, and such a matrix induces well, allows us to define a Poisson bracket on the space of densities. And the bracket is defined as in the third displayed equation. And you see that you compute the variational derivatives of the densities, and then you apply them left, right to the operator. So to the left, the bracket, the action of the operator is linear, but sorry, not just linear, it is algebraic, it's just multiplication by functions. And to the right, the operator acts with derivatives, d sigma. These are iterated x derivatives. We require that this bracket is a Poisson bracket, so we should require bilinearity, which is obvious, and then skew symmetricity and the Jacobi property. Of course, this idea of Hamiltonian operators for PDEs is how to say, it was introduced to mimic the standard finite dimensional Hamiltonian formalism for ODEs, in the case of ODEs. It was introduced in the 70s. And nowadays, it is more or less understood that whenever you have a PDE which can be called an integrable system, it usually admits a Hamiltonian formulation. Although this is not enough to say that a PDE is an integrable system. So skew symmetricity of the Poisson bracket is a property which can be read on the corresponding differential operator, which creates the bracket. And this is just a skew adjointness of the corresponding operator. Formal square jointness, while the Jacobi property is the vanishing of a certain well-defined operation between multivectors, which is called the Schouten bracket. It is kind of algebraically, it has the same structure as Schouten bracket for multivectors on finite dimensional manifolds. But here the situation is more complicated because we are dealing with differential operators, so you have to be careful. But what are Bi-Hamiltonian systems? Bi-Hamiltonian systems are systems of PDEs that can be put in Hamiltonian form in two different ways. And the two ways should be compatible. Compatibility is the requirement that the Schouten bracket between the two different operators, A1 and A2, is zero. This was a notion introduced in a famous paper by Franco Magri in '78, and usually when you have a Bi-Hamiltonian system, this is always considered to be integrable. Because under some conditions which are quite general, you can construct a sequence of commuting symmetries or commuting Poisson commuting density of conservation laws for the system which is Bi-Hamiltonian. So this, of course, mimics finite dimensional Liouville integrability. Just a remark here, this integral here with respect to the x means that the expression of the bracket is to be considered up to total x derivatives. This is just a notation. Okay, so now I would like to introduce the operators which will be which will correspond to algebraic varieties in our setting, and this will be one of the main results of the talk that I'm going to present you. Many years ago, Dubrovin and Novikov introduced a class of operators which were called homogeneous operators. They are homogeneous with respect to x derivatives. So in every summand, it is present the same number of or order of x derivatives. So you see that here you have one x derivative and one x derivative in the two summands. And the point is that if you do a coordinate change, which involves the dependent variables only, then this operator will be transformed in another operator, a different operator, but with the same form. So homogeneity is preserved by such transformations. So it's clear that these operators are, in a sense, geometric object, geometrically well-defined, and such a class. And we will see indeed that there are consequences for such operators to be Hamiltonian. Well, we can speak about this consequence even now. Everybody knows that in symplectic geometry there is the Darboux theorem, which says that in certain coordinates you can transform every symplectic form into a canonical form, which is locally constant, symmetric matrix. And here it is the same. There is a Darboux theorem for such operators, not for all operators, but for such operators, yes. And in particular, such operators, one could prove, it was proved by Dubrovin and Novikov, that for such operators, the property of being Hamiltonian is equivalent to Gij being a contravariant form of a flat pseudo-Riemannian metric, and Bij to be the contravariant form of Christoffel symbols of that flat metric, so that every flat metric admitting flat coordinates in which the metric becomes constant and the Christoffel symbols becomes 0, the canonical form is just a constant matrix eta ij times dx. The matrix is also symmetric. This is a consequence of square jointness of the operator A1. Okay, so there is a lot of geometry and differential geometry inside this operator. What was not known until, until very recently is that there is a projective geometric content into such operators. We will see it during the talk. So we will consider also higher order homogeneous operators. They were introduced by the same Dubrovin and Novikov 1 year later, 1984. And they can be found in the literature as building block of more complicated operators. As I already told, the homogeneity means that every summand has the same amount of x derivatives, and in particular A2 in this example of the general form has summands with 2 x derivatives, and A3 has summands with 3 x derivatives. So they are very complicated under the differential geometric viewpoint, even if every transformation of the type that we discussed previously transforms a second order or a third order homogeneous operators into other third order or second order homogeneous operators. But such operators admit canonical forms. We will see them after a while. Now I would like to discuss examples, and in particular examples of what we call Bi-Hamiltonian systems of KdV type. They have been first discussed many years ago by Olver and Rosenau, and they observed basically that a lot of, say, famous examples of integrable systems are Bi-Hamiltonian by pairs of operators which have the following structure. So a first order homogeneous operator and another operator which is not homogeneous. It is the sum of two homogeneous terms of different homogeneity degrees. One is of the first order and another is of second or third order. In this slide, they are named A1 and A2. The point is that the key point is that it is required that all the three operators are mutually compatible, so that the Schouten bracket of every operator with every other is 0. Now, examples of such systems with second order operators R2 are AK and S, and then two component Kamasa-Holm, Kaup-Brewer, which was described in a paper by Cooper-Schmidt in 1984, and more. With third order operator R3, examples are KdV, of course, Kamasa-Holm, and dispersive water waves. This is an example provided by Antonovich and Fordy, coupled Haridim, and more. These two last examples are two components, while KdV and Kamasa-Holm are just one component examples, while for second order, we have only two component examples for very simple reasons. You will see it very soon. So what could be a classification of such operators? In one component, it's very simple. In one component, you have only two homogeneous first-order operators. One is just dx, and the other is this Q1, operator Q1, 2u dx plus ux. And then you have only one operator of the third order. Just remind that the coefficient of the third order operator, due to square jointness, is required to be a symmetric matrix. So here it's clearly a one-dimensional, any one-dimensional matrix is symmetric. And in this case, the matrix contains just the number 1, which is the coefficient of the cube x. How to generate a skew-symmetric matrix in one dimension? Of course, this is just 0, so you don't have a second-order example in one component. So this is the simple reason why we have only, basically only this example in 3 components. And depending on how you assemble the 3 operators, P1, Q1, R3, which are all mutually compatible, you can either generate the Bi-Hamiltonian pair of the, or pencil, of the KdV hierarchy, or the Kamasa-Holm pair of the Kamasa-Holm hierarchy. And in particular, so you see that here in the first example, you have that dx is an operator which is separated from the sum of Q1 and R3, while for Kamasa-Holm is exactly the opposite. So you sum dx with the cube x, and this is one operator, and the other operator is du, sorry, this Q1, so 2u dx plus ux. Of course, we have a second, a two-component example, and this is an example of a Bi-Hamiltonian pair made by 3 operators. 2 are of the first order. They are quite simple, you can see them. And one very simple second-order operator. Basically, there is, we could prove that there is only one homogeneous operator in order 2, and it is exactly this one, up to constant multiples. So, depending on how you assemble these 3 operators, you can create the so-called two-boson hierarchy, or AK and S, or the two-component Kamasa-Holm hierarchy. Okay, so it makes sense to study Bi-Hamiltonian systems which have this structure. Now, let us discuss briefly canonical forms of second order and third order operators. They have 2 canonical forms. They have the following feature in common. They can be brought to a form where the x is factorized in the beginning of the operator and in the end of the operator. So you have dx something dx, which in the second order case is something in the middle, is just a 0 order matrix of functions or field variables. While for the third order operator, the operator in the middle is a first order homogeneous operator, even if it is not a Hamiltonian operator. It is a Hamiltonian altogether, but not the operator which is in the middle is not a Hamiltonian operator. An interesting conjecture says that this is true for every homogeneous operator, At the moment, that is known only for second and third order operators. The conjecture is, well, at least to my knowledge, is due to Mohov. Okay, so it is now it is a recent finding, the fact that the two canonical forms are invariant with respect to reciprocal transformations, which we call of projective type. Basically, we should couple a projective transformation of the field variables u tilde I into Si of uj. Si is just the linear transformation divided by a denominator delta, which is a linear form, which is the same for all field variables. This is clearly a projective transformation in affine coordinates. So you treat u1, un, the field variables, like if they are affine coordinates in a projective space of the same dimension. And you have to couple this transformation with the transformation of the x. And the transformation is simple because you just multiply the x by the linear form that we just introduced. This transformation is not integrable. So it does not integrate to a transformation of x only, of say x tilde as a function of x. It does not integrate. So it's a non-local transformation, which is known as a reciprocal transformation. They were known since ages. There are nice works of Colin Rogers in the 60s, and they are known in gas dynamics. They were used to linearize equations in gas dynamics. Okay, so well, the interesting thing is that such transformations preserve the form of operators which have dx factorized in the beginning and in the end. And this is not just reduced to R2 and R3, but we recently proved, together with Sergei Shadrin and Paolo Lorenzoni, of course, that this is also true for every operator which is factorized with the x in the beginning, the x in the end, and something homogeneous in the middle. Okay, so such operators, well, there are examples of such operators in the literature, in particular in the so-called Dubrovin-Chang hierarchy. The first operator has this form. It is a sum of terms of this form starting from second order onwards. First order is not of this form. We will see what is the, well, we are seeing now what is the action of such transformations on first order homogeneous operators. Local operators are transformed into so-called localizable operators of the following shape. So the operators are non-local. Why non-local? Because the reciprocal transformation is non-local, and it adds terms to local operators, and these terms contain d minus 1 exactly in the following shape, what you see in the slide, in the last equation. So you have this non-local term, non-local matrix Wjk, which is once to the right and once to the left of the term with the x minus 1. So every operator of this form can be transformed into a local operator using a reciprocal transformation, even if such a transformation is not always of the form of a projective reciprocal transformation. Okay. So what is the problem, mathematical problem that we considered? And well, we put a paper in archive recently, and it contains the results that I am discussing now. In particular, we will classify triples of operators where R2 is a second order operator, P1 and Q1 are first order operators of localizable type. Well, we use the name Ferapontov operators here because they belong to a general class introduced by Eugenia Ferapontov many years ago, even if such particular operators were studied in a very well-known paper by Ferapontov and Pavlov. Okay, so you have that the operator is the second order operator that we consider for this classification is a constant coefficient second order operator. So you see that the constant coefficient matrix in front of D2X is skew-symmetric. We require that the determinant of this matrix is different from 0. By the way, many of the considerations that we are making now are possible only if determinant of the leading coefficient matrix of the operator is non-zero. This is an hypothesis which we fixed in the very beginning. Probably I did not discuss it, but it was on a previous slide. And then first order operators will be Faraponov operators of localizable type. In this way, we can classify this problem, which contains as a sub-problem the classification of trios which have a purely local representative, because we can consider the situation when all operators also of the first order are local, but we cannot separate it from the situation where one of the two will be non-local, because even if we can localize one, we will not sure that by the same transformation we can localize the second one. So we classify a slightly general situation, not exactly the situation when all the three operators are local, because the transformations that we are using are very effective, but have this side problem of destroying locality. Okay. So now a bit of Plücker geometry, Plücker's line geometry. So if we consider 2 points in a projective space, the coordinates of the line through these 2 points are defined coordinates for the line with this, which passes through these 2 points, can be given by the minors of the matrix which has U and V as 2 rows. So it's a matrix which is 2 times n plus 1, and all the determinants of the minors can be taken as coordinates, even if those are too much. There are relationships between such coordinates, and the relationships are quadratic relations. So we can imagine that we are in a big projective space, which is just P of lambda 2 of Cn plus 1. And inside this big projective space, there will be a subvariety which is selected by several quadratic equations. And this subvariety is Plücker's embedding. Every point of this subvariety is a line in the starting initial projective space. Now, what I would like to show is that inside the variety of all lines of a certain projective space, we can find several classes of subvarieties, and there are specific classes of such subvarieties which are in bijective correspondence with Bi-Hamiltonian system, and this is quite surprising, and I would say that it is quite nice because it gives a totally new perspective on Hamiltonian systems, which were dealt with under the action of several groups, like okay, the differential geometric groups of the change of coordinates of field variables, or the Miura group. So a group of formal series of transformations of differential substitutions of field variables, but they have never been, how to say, investigated under this projective geometric perspective. So everything is new in this sense. So if we consider a three form in C n plus 1 star, defines a system of linear equations in Plugger space. And such a form is exactly, you see, this coefficient here. So every time we are given a second-order operator, we could prove that there exists a three-form which defines an algebraic variety in Plugger space with a system of linear equations in the Plugger's coordinates. You have to intersect this system with the quadratic relations that we were discussing before in order to have the variety. But this is how a second-order operator defines an algebraic variety. Then what we will discover during the talk is the other varieties which are provided by the first-order system and by the first-order operators, and this is new. Okay, so in our case, we have a constant matrix. So the constant matrix yields this form, and this form yields an algebraic variety in the space of lines of the projective space of the field variables. This variety is called a linear line congruence because it is a submanifold of a certain codimension of the space of lines in the projective space, and it is defined by a linear equation. At least theoretically, we should assume that the intersection of this variety with the Plugger variety of all lines is, what to say, has the smallest possible dimension, is non-singular. This is another assumption that is important for algebraic geometers, but I'm not an algebraic geometer, so I'm telling you what is happening in a, how to say, naive way, in a sense. Okay, this is all these varieties are Fano varieties. This seems also interesting for algebraic geometers. And now the results. So we can require the compatibility of a second-order Hamiltonian operator with first-order one of non-local, Ferapont of type, of localizable shape. Exactly as we have seen a couple of slides before. So this compatibility requirement, so the Schouten bracket equals 0, is equivalent to the following 6 conditions. So the tail matrix, this Wij, are constant, and then they have the symmetry property 2 with respect to the matrix of the second-order operator. Then we have property 3 and 4, and 5, which are very interesting under the geometric viewpoint. We will analyze them in the next slide. The property 6 is a property which by itself implies the fact that the first-order operator is indeed an operator. It's even stronger. Is indeed a Hamiltonian operator. This is a property which is even stronger. Together with 5, these two properties, they imply the fact that the operator P1 is a Hamiltonian operator. Okay, but this is not the main point. The main point is that condition 5 indeed is the condition on the functions gamma ijk. Ij's are two upper indices, such that these functions define a Frobenius algebra structure on the tangent space of the field variables. The Frobenius algebra means that there is a product. This product is associative, and the condition of associativity is exactly the condition number 5. Plus, there are other conditions. It is not commutative in this first algebra, but it has two interesting properties, 3 and 4. So the property 4 implies that this algebra is of the type which is called cyclic Frobenius algebra by Buchstaber and Mikhailov in a very recent paper. They introduced this definition in quite a different topic, but always inside the integrable systems. It is in a paper which is in archive. And the property number 3 is the invariance of the two form eta with respect to the Frobenius structure. Keep in mind that normally Frobenius algebra comes with a symmetric inner product, which is invariant with respect to the Frobenius algebra operation. Here we have a skew-symmetric invariant product. And in this sense, the structure is a bit less usual than the Frobenius, the standard Frobenius algebra structure. Then let us consider the metric of the first order operator lowered with the matrix of the second order operator. It is a skew-symmetric matrix. Gij is just the leading coefficient matrix of the first order operator. Okay, so we can lower the indices of Gij. What happens is that then condition 4, which is the cyclic Frobenius algebra condition, becomes the following condition. And this condition is condition under which G bar AB in lower indices is the so-called Monge form of a quadratic line complex. Now, what is a quadratic line complex? A quadratic line complex is a variety in the space of Plücker embedding, which is selected just by intersection of the Plücker embedding with a quadratic form. So you just append one more quadratic equation to the quadratic equations that define Plücker variety, and this is a quadratic line complex. These are manifolds, well, algebraic varieties, which were studied still, well, the person who introduced them, I think it was Plücker himself. But then they were classified by, well, there was an attempt of classification by Weiler, and then a bit later, 1888, the complete classification in 3 dimensions was made by Corrado Segre, not to be confused with Beniamino Segre. Corrado Segre was much earlier, active, living much before. So examples, let us consider examples. So from a paper by Cooper-Smith, 1985, we have a trio which is defined by 3 operators, and corresponding Monge metrics, they correspond to the leading coefficient matrices of P1 and Q1. And we have the following 2 Monge metrics. How to see that they correspond to a quadratic line complex? Okay, we have to use Lee's form of Plücker's coordinates. We could establish a correspondence between Plücker coordinates on the space of lines of P2. We are in P2 because there are 2 field variables. So projective space of dimension 2. So we need 3 homogeneous coordinates. 3 homogeneous coordinates are, U0, U1, U2, or U1, U2, U3, as you wish. And then we construct the space of lines. In this particular case, the space of lines is embedded into a projective space, again, of dimension 2. So everything is simpler for dimensional reasons. While if you go in higher dimensions, for example, P3, P3 is embedded into, so the lines of P3 are embedded into a 5-dimensional projective space, and so on. So dimension increases. The dimension of the space of line increases much faster than the dimension of a projective space. Okay, so this is the Lie form of Lucas coordinates. I do not have time to discuss it deeply, but it's also interesting how they are generated. They were known from even before Lie. I think it was Klebsch who first introduced them. Okay, so one can introduce two quadratic forms into this space. And, well, basically every metric that we have seen, G1 and G2, can be regarded as a quadratic form in this set of one forms. So basically a quadratic line complex is a quadratic equation in these one forms. So if you consider a quadratic equation in this one form, this is exactly given by a metric which is a Monge metric. What is the main feature of a Monge metric? Well, all of its coefficients are in lower indices quadratic functions of the field variables, but they have special relationship between coefficients, so it's not so easy. Main thing is that all the coefficients are quadratic functions. And one can express, for example, G2 as a quadratic function of these three one forms. And the interesting thing is that so Q for G1 Q has rank 2, and for G2 Q has rank 3. So Q is the matrix of coefficients of the quadratic form which represents the Monge metric. Okay. All right, so in n equals 2, we can completely solve the problem of classification. What happens is that we have the following Monge metric, G bar 1, 1, G bar 1, 2, G bar 1, 2, and the following metric for first order operators. Such metrics are linear. Such metrics, the space of such metrics is a linear space. So you can sum two metrics and obtain another metric of the same type. So there are no further constraints between the coefficients. And that means that every pair of operators which is constructed with two metrics of this type will be automatically compatible. So there is no further compatibility conditions coming from the requirement that P1 R2 Schouten bracket is 0. There are no further compatibility conditions other than being the coefficient matrix being provided by a generic Monge metric. So any Monge metric yields a first order operator in dimension 2 which is compatible with the second order operator that we considered. Okay. So yes, so this is the matrix of the corresponding Monge metric. And we can see that the coefficient C0 is exactly here. And this kind of non-local operator was introduced and studied by Mohoff and Ferapont many years ago. It is an operator where the leading coefficient metric has is in lower indices pseudo-Riemannian metric with constant curvature C0. So if C0 is equal to 0, we recover results which we obtained by computer. But in this case, the use of computer was minimal in this research, and we used more geometric intuition. So now we know the geometric meaning of such compatible operators. So how to go further in the classification? So you fix P1, and then P1 can be either of rank 2 or of rank 3. R2 is stabilized because if you make a projective transformation, then R2 will change by an overall constant. And then you can add an arbitrary Q1. And from the previous class, of course, so coming from a Monge metric, and compatibility will be automatic. So we come to the following projective correspondence theorem. So when n is equal to 2, there is a bijective correspondence between trios of mutually compatible, localizable first-order homogeneous Hamiltonian operators of Faraponov type, and R2, and pairs of conics. So C1, C2 should be of rank at least 2, because we want the operators to be non-degenerate. And now the problem is simply to classify pairs of conics under the action of the projective group. This is a work which was done by Weierstrass in 1858, 1868. So you have, coming from this classification, the set of canonical forms of such integrable systems, such Bi-Hamiltonian pairs, and then correspondingly the Bi-Hamiltonian systems, at least those coming from Casimirs with recursion mechanism. Okay, so let us see what happens when n equals 4. When n equals 4, things are more complicated, because we can, fixing a second-order operator, for example, this one that you can see, we can solve completely the compatibility equations, and we have 288 cases, which are too many to be shown here, even if I will show you examples. And in such cases, there are both local and localizable non-local first-order operators of Faraponov type. The compatibility conditions do not reduce to GIJ being determined by Monge metric. So GIJ is determined by Monge metric, but it is not a generic Monge metric. It is something. There are additional conditions. What is the geometric meaning of such conditions? This is still unclear, because it's too difficult to understand the mutual positions of the three varieties which select the integrable system. It's not also a matter of position. It could be a matter of ranks or some other geometric property which is has still not been found. So let us see some examples. So in order to write down KdV systems, Bi-Hamiltonian systems of KdV type in this particular setting, so we fixed R2, the second-order operator. The point is that there are too many pairs of first-order operators, too many compatible pairs. As I told you, there are 288 solutions of P1R2 equals 0. And then you have to, for every such solution, you have to commute it to take a Schouten bracket with another solution and see what happens and solve this additional set of constraints, which is really too much. Just to give some meaningful examples, we fixed the P1 to be an operator of this type, first order, very simple operator, since there are examples with one block, two-dimensional block, in n equals 2 case. So consider that we are not considering the case n equals 3, because in n equals 3, the leading coefficient matrix of a second-order operator would be degenerate. So we lose a lot of things, and in particular, the fact that there are more second-order operators than those with constant matrix in 3 components. So it's difficult to find all the second-order operators and give projective interpretation. And in any case, they will have a degenerate matrix, the coefficient matrix. So many things are not possible. Okay, in particular, I do not know if a projectively invariant canonical form is achievable for a non-degenerate, for a degenerate second-order operator. So this is not clear. So we fix R2 and P1, then we have to solve only for Q1. This can be done, and we found 64 cases. And in these 64 cases, we have both local and localizable non-local first-order operators of Faraponov type. Let us see a couple of examples. A first example, okay, is a purely local operator. We use this formula for the Christoffel symbols, and it is a formula which comes from one of the equations that we have seen before. So basically, the derivatives of Christoffel symbols are specified, all derivatives. So basically, we know Christoffel symbols up to a constant array, B, K, J, L. These are constants. I recall you that W, K, L are constants. So you see that these gamma are linear, and the coefficients in the linear part are just the matrix which goes in the non-local part of the operator. So if the operator is local, then you should find W's 0. And this gamma, kappa, J, L will be constants. And this is exactly what happens in this operator. You see, Gij equals all these, where the free constants are 8. And these 8 free constants, there are 2 constants which are inside the Christoffel symbols, and all the other constants are constants which you see, you have them in the matrix of the coefficients of Gij. Okay, so all Christoffel symbols, non-zero Christoffel symbols are here, and they are completely determined by the 2 constants, B112 and B131. The local cases, we are almost sure that all the local cases are contained in a quite relatively recent paper by Strachan and Shablikowski. Well, basically, this B defines what is called the Balinsky-Novikov algebra. But about the correspondence, I'm not 100% sure. This is still a work in progress. Just to recognize what are their operators with respect to ours. It seems that they are contained, properly contained into ours. And then the non-local example is here, and you can see that there are W's, W2, 1, and so on. So the only non-zero part in the non-local coefficient matrix contains 2 coefficients which are non-zero. One is W2, 1, and the other is W4, 3, which is the same. And the Wij is 0 otherwise. And you can see that there are many free parameters here, and the free parameters are all here. So again, it is an 8-dimensional space of operators. W21 parameterizes the non-local part. B221 happens inside the Christoffel symbols. There are only 2 non-zero constants, B. But the point is that the Christoffel symbols in this case are linear. This was not considered in the paper by Stron and Shablikowski. And with a few exceptions, you can see that gamma 221 is B221 and gamma 423 is B221. Okay, so in general, what can we say at this point? Well, we can say that there is a bijective correspondence within Bi-Hamiltonian operators, which are made by Bi-Hamiltonian trios of mutually commuting operators, first order, not necessarily local, but localizable, homogeneous, Feraponder type, 2 first order operators of this type, and a second order operator with constant coefficient matrix. By the way, we chose constant coefficient matrix because choosing the non-constant coefficient matrix is much more complicated. We are proceeding by steps because compatibility computations are very hard. So there is a bijective correspondence between such families of operators and trios of 2 quadratic line complexes plus 1 linear line congruence, which is induced by the second order operator, which is, of course, selected by a constant 3, 4. Now, the compatibility constraints the varieties in a way which is unclear. So, in other words, in n equals 2, we have that the fact that the metric is Monge or is defined by Monge, a generic Monge metric is enough. And that here, when the dimension grows, this is no longer enough. You have to solve other equations. They, for sure, they will give you varieties with specified some specific geometric property, mutual position, I have no idea. But this is completely unclear. It's at the moment, what I can say is that it is quite complicated. Now, what happens if we consider a third order operator? We have some results. They are even less complete. Because we know that the Christoffel symbols define a commutative Frobenius algebra, exactly as in the second order case. The difference is that the operators are all local if n is greater than or equal to 3. Keep in mind that R3, in our case, is again a constant coefficient operator of the form eta ij times d cube. So also here we are quite limited in the shape of the third order operator, because otherwise computations become very complicated. If n is greater than or equal to 3, then we could show that any commutative Frobenius algebra determines a solution. And this, I think that this is probably a result which was already found by Stron and Szablikowski, but they started with a constant coefficient Christoffel symbols, so Balinsky-Novikov algebra, while we proved that if you start from our projective classification problem, you come to such a shape only in the case R3 constant coefficient operator with non-degenerate matrix. And by the way, the fact that such operators define a commutative Frobenius algebra was independently proved by Bolsinov, Konyaev, and Matiev in a paper which you can find in arXiv. It is one of the series of papers about 9-house geometry. I don't remember, maybe 3, maybe the third paper. You can understand the fact that in the third order case, we still do not have a projective interpretation of the first order operator as a projective submanifold subvariety in Plucker space. This is still missing. So there are lots of problems in this how to say, in this stream. So conclusions, okay. Then what happens now that we know that there is some projective geometry in the integrable systems which have the structure that I have discussed? Well, I have no idea. But I can just say that the geometry is nice and it is interesting to go more deeply and see what happens. It's like a movie. I would like to see some end at some stage. Okay, thank you very much for your attention.
Thank you, Raf, for a very interesting talk. Questions, remarks? Okay.
Raffaele, may I ask one question?
Oh, yes.
Can you hear me?
Yes, yes, of course.
Yeah.
Hi.
So if we consider, say, a third order operator,
Yes.
then in canonical coordinates, it corresponds to a quadratic line complex, right?
Yes.
Suppose it's compatible with a first order operator.
Yes.
So is it correct that the metric of the first order operator is also Monge, or it's not true?
I do not know, unfortunately. I cannot, I don't know, I have no idea at the moment.
There is no such statement. All right, all right. Okay.
No, what I can say is that for second order operator, this is true if the second order operator is constant coefficient. By the way, I would like to add the fact that the metric of first order operator in that case is Monge, but it is not a Monge metric which also defines a third order operator.
Okay, okay. Thank you.
Thank you, Zhenya. More questions? Okay, Raf, thanks a lot again.
Thank you very much, Joseph. It's always a pleasure.
Yes, for me too. So we still don't have a program for the next Wednesday, but we're working on it. And well, thanks for joining us, and goodbye, and have a good week. Bye-bye.
Bye-bye.